Hello students, today we are going to solve a question from CSIR NET 2020 and question number 45, and this is basically from atomic physics. In that question it is mentioned that the wavelength of first line of Balmer line for hydrogen atom, it is mentioned that is 656 nanometer. Now the question is the wavelength of hydrogen like atom having atomic number 6 and nuclear mass is mentioned as 19.92 into 10 to the power minus 27 kilogram. Okay, for hydrogen atom it is provided the first line of Balmer series having wavelength 656 nanometer, and for hydrogen like atom having atomic number 6, nuclear mass is 19.92 into 10 to the power minus 27 kilogram. For that hydrogen like atom, you have to calculate the wavelength of first Balmer line. So as you know that wave number, there is nothing but inverse of wavelength that can be represented as R infinity into mu by me into z square, then 1 by nf square minus 1 by ni square. And of course, for Balmer line, that final state quantum number is nf equals to 2, and ni can take values 3, 4, 5, 6, and so on. So for first Balmer line, that ni will be 3, and for Balmer line, nf is fixed, that is 2, right? So I can, in fact, I can write this wavelength or 1 by wavelength of hydrogen atom that will be containing one proton, that can represent as R infinity into reduced mass of a hydrogen atom. If you see the structure of hydrogen atom, you have a one proton sitting at the nucleus and you have a one orbiting electron. Okay, so obviously reduced mass of this system will be mass of proton. As you know that mass of proton is nothing but 1836 times mass of electron. So you have a two particle system having mass 1836 times mass of electron and mass of electron here. So I can calculate the reduced mass, then that will be nothing but m1 into m2, that will be 1836 times me square divided by m1 plus m2, that will be 1837 times me, and you already have me here, so that will be me square. And of course for hydrogen atom, z will be on, so on square, that will be on, and you will have 1 by 2 square minus 1 by 3 square. And let us take this is your equation number 1. And similarly, for hydrogen like atom, Z will be 6. Now see that nuclear mass is given for hydrogen like atom. In fact, I can calculate the mass number. So mass number will be how much? If you have a total mass, that is 19.92 into 10 to the power minus 27 kilogram. So if you divide by this number by mass of proton, that is 1.67 into 10 to the power minus 27 kilogram. So if you divide, you'll get the mass number of this nucleus. If you calculate, you'll get approximately this number close to 12. So it means that if you make the structure of hydrogen-like atom, you will have 12 6 proton and 6 neutron is sitting at the nucleus, and you have an orbiting electron. So obviously, if you write that wavelength, okay, if you write that wavelength of hydrogen-like atom, I'll write inverse of wavelength of hydrogen-like atom having total number of proton 6p, that can be represented as infinite nuclear mass required constant, and then you have a reduced mass. Now see here, the reduced mass will be total mass of nucleus that contains 6 number of protons and 6 number of neutrons, and you have another particle electron. As you know that mass of neutron is almost close to mass of proton. So I can say that total mass of this nucleus will be 12 times mass of proton. Now I can calculate the reduced mass of the system. That will be how much? That will be 12 times MP, and MP can be written as 18 36 times me, and you have another me, that will be me square. So this is like m1 into m2, and then you will have m1 plus m2. m1 plus m2 will be how much? So you'll have m1 is how much here? That will be 12 times mp, right? And then you'll have me. Okay. So in fact, this number you can calculate. So this thing I can represent like 12 times mp. mp I can write, that will be on 836 on 836 times me, and you have another me. So plus on, I can take me common, and in the denominator you have another me. So that will provide you me square. So this will be cancelled, and then you have z square. Z square, that atomic number, that is 6. So z square will be 36, and then you have 1 by 2 square minus 1 by 3 square, because this is also they ask for first Baumol line. Okay. Okay. In fact, this number, if you see, this number is much greater than on, right? 12 times on 836. So you can, if in fact you can approximate this. So it will be like r infinity, then you'll have 12 times on 836 divided by 12 times on 836, because this number is much greater than 1. So of course you can calculate, but you can approximate also. That will give you more close result. That's not a problem here, because this number is much greater than 1. Okay. And then you have this factor 36 and 1 by 2 square minus 1 by 3 square. Let us take this as your equation number 2. As you know, this wavelength is provided for hydrogen atom, that is 656 nanometer. Now if I divide equation on equation 1 by 2. If I divide equation 1 by 2, then basically I'll get, on the left hand side you will have lambda into 6p, that we have to calculate, divided by lambda for hydrogen atom. That will be, you can see here, this will be cancelled, right? This will be cancelled. Okay. So as a result, what will have, you will have only, everything will be cancelled here. You will have on 836 divided by on 837 into 36. If you cancel, if you simplify it, you will get this factor, on 836 divided by on 837 into 36, and everything. This will also be cancelled. This will also be cancelled, and all other parameter will be cancelled. This will be the remaining. It means that wavelength of first Baumol line for hydrogen like atom having atomic number 6 can be written as lambda wavelength for hydrogen atom, that is given, right? 656 nanometer into on 836 divided by on 837 times 12. So if you simplify it, you'll have on 8.2 nanometer. So this is the wavelength of first Baumol line for hydrogen like atom having atomic number 6. So this will be the correct option. And in fact, this is a very interesting question. In recently in TIFR also, they ask similar type of question. Okay. So please solve this question accordingly, whatever step or concept I have told. Thank you.